Now it's looking okay. Welcome to another exciting Java class. This is our last class in biomedical imaging, and isn't it? This is the last class, and there is a final, and it is due on the 2nd of May, and the final is due at 11:30 a.m. on Friday, May 2nd, according to the registrar. I have no control over when these things are due. As a result of a conflict in my class, I am unable to attend the final because they have scheduled the final at the same time as another final.
You can't go.
I can't go, so I will not be here. So you can submit the final electronically. I called the registrar's office to complain about the situation, but no one will answer the phone, and no one will return my call. I tried another person at the registrar's office, and she's gone until after the semester ends. So, as a result, I have little or nothing to do with the schedule. It's scheduled when it's scheduled. I called Annette and asked her about it. She said, I have no control, blah, blah, blah. And I said, neither do I. And so there it is. So your final is due without extension at 11:30 a.m. You do not have to be here for it. You merely need to submit it. Moreover, you can submit it early. But you may only submit it once. Well, it's 7 days, but we talked about it like the week before last. Well, I had discussed the edge detection with you, and I gave you the assigned reading. And moreover, I'm providing you with a solution to the final, which is in Pascal. And what I can do is I can review the Pascal solution with you, if you like. This is a solution which I wrote myself back in 1987. Back in the days of yore. Back when the rock was hard. Back when the metal was heavy. Then I had, got involved with image processing, and there was an image processing lab. We don't have that anymore. It became a center for image processing and then went out of business. And so did the Homedale office of Bell Labs, by the way. It's a ghost town. So, someone had said, what is the point of converting an image into a vector from a raster? And the answer is, if you want to cut an outline with your laser cutter, you need a vector, not a raster. Because what is happening with the raster scan is you go in raster scan order, which is left to right, top to bottom, and you output a pixel whose value is represented by a color. And what happens with the laser is it's either going to cut or it's not going to cut. And what it's going to want to do is cut in minimal time, especially in a production setting. So you don't want it to just cut one little tiny pixel and then scan through the whole image left to right, top to bottom. You want it to follow the contour of the thing you want to cut. This will minimize the amount of time it takes to cut out an outline and do production. So as a result, not only do you want to edge detect your image in order to be able to make sure that it is either value 1 or value 0 or value 255 or value 0, you also want to arrange the points on the image to minimize the amount of time it takes to cut the outline. So in terms of a pen plotter, this would minimize plot time. So what we can do is we can think of a laser cutter as a pen plotter, where the pen is a laser that runs at a frequency of approximately 1090 nanometers, a wavelength of 1090 nanometers, which is infrared, and which can output a power which ranges from a few milliwatts to a few gigawatts. They have one that does cut through titanium out in the Hartford Precision Center near Pratt & Whitney, and it's really a sight to behold. And it's used in the aircraft industry. So you can cut through really heavy-duty metal. You can cut through plastic and get a finished edge, no deburring required. And what we can do here in our program, because we're going to be programmers for this, is we can output a format which is compatible with the laser. And the format that the laser can read, or that the application which can drive the laser can read, is called Scalable Vector Graphics, or SVG. And SVG format is really a very common format. It's a standard format. It's a World Wide Web Consortium international standard format, and it is a format that we can output with our Java programs. Moreover, the vectors that we extract from our edge-detected image will have to be ordered in order to minimize the plot time. And the ordering of the vectors is one of the post-processes which I'm endeavoring to solve here in the raster to vector conversion with vector ordering post-process. So it's one thing to convert a raster to vector, and it's quite another thing to order the vectors in order to minimize the amount of plot time, or in our case, cut time. So by the time we're done, we're going to have little programs which can output something that can be cut with a laser. How cool is that? Sweet, right? Yeah, very sweet. So one of the things I want to do is I want to define clearly the input and the output. So I've created a program here called XY2Vec. And what it does is it takes a list of XY coordinates, and you get those XY coordinates by going through your image, edge detecting it, and then extracting the XY position of every pixel, which is not 0. And if you're edge detecting, presumably that pixel will have value 255, 255, 255, which would be a white pixel on a black background. But you could do it the other way, a black pixel on a white background. It really doesn't matter. They're equivalent. The edge has to be good. If you do this whole thing with garbage in, you're going to get garbage out. So what that means is you cannot have spurious speckle. You cannot have thick edges. So what we're looking for is a speckle-free, edge-detected image with single pixel width-wide edges. Single pixel width-wide edges means not thick edges. So that is very important. Then once you have your single pixel width-wide speckle-free edge-detected image that you're happy with, that's when you can proceed to output vectors. Once you have your vectors, and the vectors will consist of a series of line segments. A line segment consists of x1, y1, x2, y2. And the x1 and y1 are in pixel coordinates, so they're integers. And the x2 and y2 are in pixel coordinates, so they're integers. And that's what a vector looks like. Now, when you come across another pixel that's on, you may look through your list of vectors, and you can add the pixel to that vector by extending its tail. So you start with a head, and you look for pixels that can accommodate the tail on that vector. Presumably, your first pixel will be the head. The next pixel that you encounter will be adjacent to the first pixel. You can look around, or you can look at all possible pixels. Or you can organize the pixels. How would you organize the pixels in order to minimize the amount of time it takes to find an adjacent pixel? Okay, let's start again. What would an adjacent pixel be? Say it again? Next to it. So let's assume that the pixel value is x comma y. How would I define an adjacent pixel? Yeah, so if I had, I could define it. We can do it in any one of a number of ways, but I could probably guarantee you that. Let's see, how shall we do this? I'm just thinking out loud. I'm thinking maybe I should just create a little PowerPoint slide on this, but we might already have something. ECE 311. Do we have anything on boundaries? We did edges. We didn't do boundaries. I don't know if we did boundaries. Yeah, we did this. What I wanted to do was something about raster to vector. So why don't we do the following? Copy, paste, and what we'll do is x, y to vec. And we'll make a little display out of it. So, xy to vec is the title. So, xy is, let's see, we'll make another one. Given, let's see, I'll do it this way. Problem statement. Given a set of xy points, find a set of vectors that spans xy points, and I will call it S sub p, that spans S sub p. So a set of vectors V that spans S sub p. How's that? So now let's assume that vectors where V consists, where a vector is defined as x1, y1, comma, well, I guess we'll put it in parentheses. Or maybe we'll do it like this. How about this? Parenthesis x1, oh, I know how to do it. p1, comma, p2. Where p1 equals x1, comma, y1. That's good, actually. I like it. And where p2 equals x2, comma, y2. Fair enough. And so I have a set of points, xy points, set of points, xy points, S sub p. Alright, so that's fair. So every p sub I in SP will be covered by V. So that is to say that as you proceed to build up the vector data structure, you will subtract from S sub p the points in the list. Once you've done that, once you've created your set of vectors, you're done with problems x, y to vec, and then you're ready for the vector ordering. So the first thing to do is, how do you create your set of vectors so that they are minimal in number. That is, the cardinality of V should be minimized such that the cardinality, that is number of elements, of V is minimal. Does everybody understand the term cardinality? No. Cardinality of a set. Let's assume I have a set of numbers, 1, 2, 3, 4, 5. What is the cardinality of the set of numbers? It's 5, the number of elements in the set. Let's assume I had a set of 3 numbers, and the numbers were all identical. The cardinality of the set is still 3. So I don't require that every element in the set be unique, but when I have a set of points that come from an edge-detected image, the set will be unique. That is, no 2 points will be the same. So there are several strategies for accomplishing, for solving this problem. Okay. First thing is, you would like to organize the points so that you can find points that are adjacent to given points. So how would we proceed through that problem? Any ideas to organize the points? Or do we need to define what adjacency is some more? Let's start with that. What is an adjacent point? Okay. P1, let's see, adjacent P1, comma P2 equals true if the distance from P1 to P2 equals 1. How's that? Is that a fair definition? So suppose I said I have a point 1, 2, 0, comma 1, 3, 0. Let's call that point P1. And let's make this the x and the y coordinate. There will be 8 adjacent points. Okay. They will be north, south, east, west, northeast, northwest, southeast, and southwest. 1, 2, 3, 4, 5, 6, 7, 8. Okay? That's fair, right? All the coordinates of the compass. And if we decide that we can label these points P sub n, well, that will be equal to 1 point north, 1, 2, 1, comma 1, 3, 0. P sub s will be 1, 1, 9, comma 1, 3, 0. No, I got it wrong. That's the north one. This is going to be 1, 2, 1. That's going to be the east one. And the south one, it's down. It's over by to the left. So we'll call that west. So that's my example. East and west are left and right. So I incremented the x-coordinate, decremented the x-coordinate. I can increment the y-coordinate, decrement the y-coordinate. I can increment the x and y-coordinate, or I can decrement the x and y-coordinate. I can do all the combinations of increment and decrement and search around the adjacent square. So is that clear? Do we now understand what an adjacent point is? So to create a vector from a single head, right? P1 and P2, both adjacent, I can create a vector which will consist of a head, that is P1, and a tail, that is P2. The other thing about this vector is it has a slope. And that's going to be delta x and delta y. And so if you find another point that you would like to add to vector v sub I, it had better not change the slope. Otherwise, if it does, you better start a new vector. So I can extend v sub I if the slope does not change. Otherwise, start a new vector. So what's the other condition? The slope does not change and, well, I can extend v sub I with another point. I'll call it extend v sub I with point P3. If the slope does not change, if P3 is adjacent to P1 or P2, and the slope does not change. Otherwise, start a new vector. Got that? It's clear, right? If you're going to try and create a chain of points to create a line segment, the line segment has to stay straight, or else the line segment will not be a line segment, it will be a curve or a shortcut across an arc. And you don't want that. If you want to follow the arc, you're going to need a series of line segments. Is there a question? So this is the essence of the program that I created called XY to vec. Right? XY to vec is described in Pascal. Well, it's described in here. P-code summary. For each point in the list, do stash the point. And what stash a point does is it tries to stash a point in an existing list of vectors, and if it can't, it starts a new vector. That's key. So you got this big list of vectors. For each point, you have to search the vector to see if it fits. If it doesn't break the slope tolerance, then try to stash the point. And if it does, if the point can't be stashed, then you create a new point, and the new point will go into the head of a new vector. So try to stash a point stashes by looking at every single vector. Looking at every single vector, and it goes in an order. How do I order the list of points so that I can minimize the amount of time it takes to see if there's another, if the points are in order? Is there some way to order the points to minimize the amount of time it takes to put them into the vectors? What would be a good way to do that, do you think? How can I ensure that the points will have some coherence? Yes, sir. Well, if I iterate through the image in left to right, top to bottom order, I can get a list of points that way. And the points will come in, but they'll come in scanline order. So if I have sort of a trapeze, I could get the left side of the trapeze and the right side of the trapeze. The points won't have any coherence. So if what I want to do is I want to just leave the points in the image and scan the image and take the points straight out of the image, I could do that. Or I could take the points as they come off the image and I could order them somehow. How could I order the points?
How sorting order?
Well, if I sort the points in horizontal order, that might be good enough. I could sort them in vertical order. That might be good enough. Yes, sir.
I'm just listening and mapping.
I could go in scan line, left to right, top to bottom, but isn't that the equivalent of sorting them in vertical order? And in fact, I'm sorting them in vertical order and then by horizontal order if I go left to right, top to bottom. So in fact, they are already sorted as they come in, at least in terms of top to bottom and then from left to right. So they're already sorted in a sort of order. They're already sorted. What else could I do?
Left to right and then backwards.
Left to right and then backwards?
Yeah, just
In other words,
going
sort
back
them
and forth.
horizontally and then sort them vertically?
Only horizontally, but well, yeah, horizontally and vertically. But instead of like reading ahead, instead of going backwards and forwards, you just go left to right and then again right to left. So you're not wasting the time.
How about this?
Double time.
How about if you start with a point, and instead of scanning all the points left to right, top to bottom, you just look around in the immediate neighborhood of the point. And then if we find something, then we can continue to follow that point along the image. And for each point that we take out of the image and incorporate into our vector, we can set it to the background color. That's called the bug walk algorithm. The algorithm which I used is a brute force algorithm that just iteratively searches through all the points and continues. So I have two approaches to this. One is I'll call them two algorithms that might work. Okay. First, list all the points for each point in the list, stash the point. Okay, I'll call that, I don't know, what shall we call it? This is the brute force. Yes, sir?
When you say stash the point, you just mean like an array or something?
You're going to put it into, stash the point in the vector list.
Is the vector list just like an array? Like what is the vector list?
It's a list of line segments. I'll call it the line segment list. The list, oh, I know, stash the points in V. Right, so we define V as a series of head and tail elements, V sub I, where the number of different vectors is not known in advance, and a list of all possible vectors will be, how shall we call it, null.
Is that list just like an array?
Could be. You could put it in an array, but arrays don't typically get expanded except for array lists. You could probably store the line segments in an actual vector container that can be expanded. That is like a java.util vector or an array list.
Is there a class for that?
Java util vector? Yeah. Yeah, there's definitely a container called vector, but it's got nothing to do with the vector I'm talking about here, which is just a line segment.
So it's supposed to order them?
You're supposed to order them.
But that would order them? Just stashing them?
No. Ordering is a post-process.
Okay, so we're just trying to gather all that.
You're building vectors from a list of points.
Okay.
Or I should say building line segments, because vector is the name of a class. But when you read this paper, you'll see the term vector, but the paper is written in Pascal and had nothing to do with Java, because it was written long before Java existed. I beg your pardon?
Looks like it's on a typewriter.
It was actually printed on a spin writer, which is an early form of word processing. Before there were laser printers. It's an impact printer driven by a serial port. The brute force algorithm works. Always works. It always converges in an amount of time which is n squared. I'll call it order n squared time. Frankly, I don't care that it takes order n squared time. That's okay. It's okay with me. There are interesting and wonderful ways to make this search for adjacent algorithm points faster. One way is you can use a grid. But we don't have to care about making the search faster. Right? We don't have to care about it. Gesundheit. So we'll call this, I don't know, algorithm 1. Next algorithm, the bug walk algorithm. Walk around the perimeter of the outline of the edge detected image and build the data structure and build V. Now the nice thing about going on the outline is you're only searching for points that are adjacent. And so what you're doing immediately as you walk through the image is you're going to just search the immediate neighborhood, which consists only of 8 different possible point directions, compass points. When you search the 8 compass points, if nothing is on, you're done. Plus, if you have a point that you've already considered, you can set it to the background so it doesn't get considered again, instead of trying to remove things from a list. So that can be used to extend your list if you like. Couple of ways to do this. Do I have another algorithm? Is it a better way? Maybe. It depends on the image. When will this not work? Then after you've gone through and done your bug walk, right? Now suppose there are still points that you haven't seen. Now you have to continue to go and resort to the brute force algorithm later. This leads to a hybrid algorithm that falls back to brute force when lines are discontinuous. Got it? So that bug walk algorithm is an interesting way to go, but it's not necessarily the way to go. Now you've got your vectors, but the vectors are in perhaps a non-optimal order. They're not laid end to end. What will happen if the laser starts to cut vectors? It'll cut one here, then it'll turn off, go all the way to the other side of the image, cut one over there, then turn off, go all the way back to the other side of the image, cut a little over there. Because the vectors are not in order, it will take forever to do a cut. So what you really want to do is lay the vectors end to end. That's called the vector ordering post-process. Laying the vectors end to end does not change the number of vectors. So here comes the post-process. Vector ordering. Given a list of vectors, find a way to reorder the vectors to minimize the plot time, or in my case, the cut time. So what that's going to do is this will minimize the amount of time the laser is off. The same thing can be done with any vector output device. For example, some people have laser shows where the laser is not used to cut but instead used to project, and the laser bounces off two galvanometer-based mirrors, and the mirrors deflect the laser in the X, and then another mirror deflects the laser in the Y. And then this allows you to draw on the wall. But because of the limit of the speed and bandwidth of the galvanometers, you're limited to the number of vectors that you can draw before you start to see flicker. And so as a result, you want to minimize the amount of time spent with the laser off. And so this is the same exact problem. Minimizing the amount of time that the laser spends off is going to essentially allow you to maximize the number of vectors that you can draw without flicker. How's that grab you? So now the question is, what's the algorithm for vector ordering? Can someone think of an algorithm? Insertion sort. That might be good. So here's an algorithm from Brian. Tell us about this algorithm that you have. I'll call it algorithm B for Brian. No, I know. We'll call it algorithm 1.
Well, I'm pretty sure quicksort would be better if we're looking for something more.
What are you sorting?
Just an array.
An array of? An array of pixels. You don't have pixels anymore. You have vectors. You're sorting vectors x1, y1, x2, y2, and a slope.
Start point and end points.
You have start points and end points. That's what you have.
Is this an array of data, though?
Well, sure. Okay, it's an array of data.
Can we quantize the vectors into some numerical value and then sort of we get one, like, it boils down to some numerical value?
So you would like to create a hashing function that takes the x1, y1, x2, y2 and gives you some number? Okay, I'll buy that. And what's the hashing function doing exactly? Distance away from?
Some constant point, I guess. Quantizing the different vectors so that they're relationally different from each other, and then you can sort of. That's the idea.
So here's a vector, and here's another vector, and here's another vector. Now, wouldn't it be nice if this vector were drawn first, and then that vector, and then this vector? In other words, I'd like the head of this vector to end where the tail of the prior vector begins. So if I wanted a vector ordering algorithm, it would be this way. 1, 2, 3. Yes, sir?
What order is it normally in?
We don't have a normal order. It could be in any order. We don't know. But by the time the laser is done, we'd like to make it so that it can plot the vector without lifting its pen.
This is a traveling salesman, right?
Yeah, this is called the Chinese postman problem.
So there's no like default order necessarily.
Well, here are the vectors. I just drew them in a random order. Now, if I want to draw them and minimize the amount of uptime, I might go like this, then like that, and then like this, and then like that, and then like this, and now what? Oh, I've got to lift up the pen, and then turn it down, and then go like this, and like that, and like this. So is there a way to draw this figure without lifting the pen? What if I went like this, and then like that, and then like this, and then like that, and then like this.
It's discrete math.
It's a discrete math problem?
Yep.
Okay. Which problem in discrete math is it? It's a Hamiltonian thing. You mean it's an Eulerian path? It's also known as the directed Chinese postman problem because you don't want to visit the same place twice. And here is a paper on the directed Chinese postman problem. And what it does is it gives us an abstract graph theory answer to the result, and it even gives us a least cost path in Java. The Chinese postman problem, also called CPP, has been widely distributed on the web with a solution. Interestingly enough, I thought it would be fun to download it to see if it was useful for anything other than sort of giving me a headache. And here it is, the Chinese postman problem. Now, the way they structured it is they gave us a series of arcs and vectors, and they decided to, I don't know, Chinese postman problem. You can Google it and download it and try it. I would wholeheartedly encourage you to look at the paper and decide whether or not this is going to be of any use to you. I looked at it and thought it's such a graph theoretic approach that it will be useless for image processing students. And I don't want to discourage you, but I feel if you go into it deeply, it will distract you. On the other hand, I would be happy to be wrong about that. I've got the paper here. I'll pass it around. I'll let you Google it. I don't encourage you to ignore it completely, but I think aside from being aware of it, it's not going to help you. I know it didn't help me at all. I looked at it, and after I looked at it for a while, I said, why are we doing this way? This is for graph theoreticians. It's not for image processing people. That's the way I saw it. So, I mean, it does solve the correct problem, and it is giving us an answer. It's not the way I would approach the problem, so let me not encourage you to ignore it, but I don't want to encourage you to get real distracted by it either. I don't know if that makes, sometimes mathematicians come out with very elegant solutions. This ain't one of them. It is NP complete no matter what you do. It is as hard as any problem as the traveling salesman problem.
The thing about NP complete is that they can't prove that there is no lowest efficient solution. So that's like I should try and.
I will prove to you that this is NP complete.
Oh. No, you don't have to.
I will prove it to you with a graphical argument. Proof of NP completeness. Suppose I wanted to find the shortest path between 2 points, and there were obstacles. Okay? Obstacle 1, obstacle 2, and obstacle 3. And I have a start point. Here's the start point. And here is the end point. Here's the end point. How many different paths could there be? Well, I could start here. I could go up, 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 and then down. Or I could go up, and then down, 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 and then up. Or I could go up, and then down, and then up, and then down. In other words, all possible permutations for navigating across these different points. Now let's assume I take the number of obstacles and I increase them by 1. Okay. Now how many paths are there? Well, in fact, there are exactly 2 to the n number of paths, where n is the number of obstacles. And that makes this an NP-complete problem. And I think you can easily prove it to yourself. There are all the different possible permutations of going around all the different possible paths. Just add one more, and you'll see that you've doubled the number of different paths each time you add one more obstacle. by doing that, I can claim that there are exactly 2 to the n different paths, and n is the number of obstacles. So that proves NP completeness, right?
Non-polynomial,
Right? It's not a polynomial, it's exponential.
Yeah, okay.
It's exponentially hard. Exactly exponentially hard. When posed in this way. So the shortest path problem is non-polynomial complete, and provably so. In fact, they say it's as hard as any problem in p-space hard, polynomial hard. So I think that gives us a good feeling for the hardness of this problem. Now, having said that, I don't care how long it takes to solve the problem. I just don't care. I know it's a hard problem from a computational point of view. I don't care if it takes you a minute or two to sit there in terms of CPU time, because optimizing for this is much harder than just solving it. So brute force is the way to go. Get a solution. Don't make it fast. Slow is okay. Slow and working are great. Fast and broken is bad. Right? So make it work before you make it fast. So what is the, I'll call it brute force. Doug's dumb brute force algorithm. Algorithm DDBFA. Or perhaps that's redundant. Algorithm DDBF, version 1.0. That's Doug's dumb brute force algorithm. Well, my algorithm says this. Given for each vector, examine, well, look, stash for each vector in V, create a list of, I don't know, for stash, for each vector in V, stash the vector V sub I, for each vector V sub I in V, stash the V sub I in one of several lists, or create a new list. So what we're going to do is have a list of vector chains, where each vector chain consists of vectors that are concatenated with respect to one another. So the way I like to think about it is the output will be a set of vector lists, each one of which will be will contain connected vectors. So while the different vectors will have different slopes, they will have their heads and tails concatenated. That's vector ordering. So when you go back and you look at the list of vectors in the vector ordering, and you can see where it says takes order n squared time. Now comes the ordering. And yes, it's NP complete. Let's see now. Presumably CPU time is always going to be faster than laser cut time, especially when you're starting to do production and you're doing this over and over. So let's see now. Somewhere in here I have some P code, and here it is. For the next output vector to the total number of vectors, so these are all the input vectors, move the input vector to the next output vector. That's taking the vector from the list, putting it into the next output vector, changing the current vector into the next closest output vector. So you got to search for all the different vectors that are in the output vector list, and then you got to put it into the list. Somewhere in here, techniques for improvement. What's going on? I was thinking about using grids. And in fact, grids are a standard way to approach this problem. And then at the end comes the Pascal.
Are we supposed to know how to read that?
Well, I've got a data structure here called slope type, and you could probably create a class called slope type, which consists of two values, the change in x and the change in y, because that's all you need for the slope. You don't have to do the division, because you might have 0 when you do the division, divide by 0. The point type, that's x, y, and I'm using values that range from 0 to 511 because I was working with an image that was coming in off a camera, which only had 512 by 512 pixels. And then the vector, I got a head and a tail, and you can extend the tail or the head as long as the slope, the initial slope, which is obtained from a single head and a single tail, doesn't change. And then if the tail is empty, because you've only put in a head, then the next time you get an adjacent point, you can establish the tail and then set the slope. So this could become a, what do we call it, a class. So these records are really just data structures which could be used inside of a class. In fact, Java already has a point class, and the point class is in Java awt.point. Further, if you wanted to, you could use that point or not, depending on what you want to do. Let's see now. This is just reading in the data. This is doing the big search. I think reading it may or may not be of much use to you. I doubt that you would want to try and translate this code straight into Java. In fact, I would recommend against it. It's not object-oriented. It uses procedures, it uses functions. Actually, functions aren't too bad. Functions return values. This is giving you a distance. It's computing the distance in the usual way, x squared plus y squared. Let's see what else we need in here. Here's some examples. When this was done and it was ordered, it would go nicely around the edge, and then it would lift up the pen and do the two insides, and then it would lift up the pen and do the main inside. So you couldn't have everything connected. This is supposed to be an eye. Here's a coastline. And here's a more complex image. And here you can see there's lots of interesting speckly parts that were included. And of course the pen would have to go all the way over here and draw, and then go to the nearest neighbors in order to be able to complete the circuit. And here's another image. This one is of a reflected ball. And you can sort of see a person in here talking to another person there. And then what I did was, yeah, that's a Brian Eno album. And here's the number of vectors for the different figures, and the amount of time it took to do the computation. And you can see it got quite lengthy. And here's the vector ordering, also order n squared. The n squared part is this nice smooth line. The actual data is the x's. And this is the plot time to compare ordered time versus unordered time. So here in Figure 5, we could greatly reduce the plot time when we order the vectors. And that's the dealie. So then, let's see now. Other things you will need to look at, perhaps, if you go into my code and you take a look at how, sort of things are working for me, you'll see in the IP GUI frames boundary frame, I've got an implementation of a bug walk algorithm, which is kind of slick. And what I do is I start with my little hardware.gif, which is already a black and white image, and then I proceed to draw the polygons that I'm able to extract from the boundary. Let me see if I can get this to run. So what you see here is the original image with a not too well done edge, but not bad. It's single pixel width wide edge detected image. The edges look like they have been distorted relative to what I would consider to be a good outline for the bolt. I'm not exactly sure why my edges don't look a little bit better, but aside from that, these are the polygons that you get. I'm drawing them in a green outline around the side here, and these polygons are how do you call it, part of a data structure called polygon in the java.awt. So there is a Java AWT polygon, and in fact, if you have an instance of this polygon, you can pass it to the graphics context and call draw polygon, and it will draw the polygon right into the graphics context. So what I did was I got the image, displayed it, got the graphics context off of the image, and then drew the polygon straight onto that image. In the background here, you can see the actual geometry for the vectors, which is kind of cool, actually. So, I guess the first thing you'll want to do is you'll want to edge detect your image. What I did over in here was I have this thing here called get single pixel edge, and that was done after a threshold. One could make a compelling argument that threshold may not work for your image, but it worked okay for mine.
You were starting with an edge detected image,
No, you don't have to start with an edge detected image. Let's start with a
for the assignment. I thought that was the idea.
you will edge detect your image.
Just doing it with the software.
Well, presumably you will use some kind of
No, like just
technology.
the J2D.
You may want to use.
Because I think we just I thought for the homework we were just supposed to alter it with the program that we have, as opposed to actually do it in Java programming code.
Well, you will need to edge detect the image. I don't know how you will do it. Here is the hardware that I used. Right now, if you look at that, and you go through and you do, maybe there's a better way to do this. I'm not sure. I did a thing with thresholding, but I'm wondering if there isn't a nice color quantization algorithm that would work for me here. So here it is to 64, 32, 16, 8, 4, 2 levels. See now what happens at 2 levels? You lose the cap on the bolt. At 4 levels you get it back. This is why thresholding didn't work very well for me. So at 4 levels, if I applied the change, and then I did a
When you filter, you said about edge. Was that what you did?
I beg your pardon?
I'm sorry. Under filter,
Uh-huh.
edge.
Here's edge. I could just try and show some of the edge buttons here and try a variety of different edges, but you can kind of see they're oriented edges here. These are anisotropic edges. Right? Lap 3 is an anisotropic edge, which means not oriented. That's not bad actually, because you got the cap right in there and the part that goes across. I don't know if you could see it okay. Hat 13. Oh, that gives me a very nice edge. So it's not a single pixel width wide edge. That's the Laplacian of Gaussian, the hat 13. That's the sombrero. Here's a Laplace 5. That's pretty good. Here's Laplacian Pruitt. And there's a Sobel. And we can apply a Sobel with a different size that negates it. You know, you may have to screw around a little bit, find out what works. Here's Laplacian of Gaussian plus a Sobel, all built into the same. It does a threshold as well. That's not bad, actually. Does this do anything? Oh, I have to apply? Maybe I could do a comparison. Turn off the Sobel, turn off the threshold, turn this on. It's not updating. I may have to apply. Oh! That wasn't so good. So the question of exactly how you're going to do your edges, I don't know. If I go into this now and use my little edge buttons, that's pretty good right there. Apply the change and then do a histogram equalization. Whoops. There, yeah, something's going on here I'm not quite understanding. Why wouldn't this histogram equalization give me the, maybe I need a threshold in here. There should be a color threshold filter. Here it is. Threshold panel, adaptive threshold. Perfect! Just what I'm looking for. It's just a little noisy on the edges. So I would redo this to get rid of the noise.
And the log Sobel work well.
Yeah, I could redo it and do the log Sobel. Well, I can tell you what I ended up doing after some experimentation, although I wasn't particularly happy with the result at the end of the day. I called get single pixel edge after a threshold. And that uses a morphological image processing algorithm. It does an open and then a close. It gets an inside contour. I think I assigned that as reading. Could it have been chapter 11?
You signed 7 and 10.
Really?
Or just 10.
Yeah, here's 10. Read 10 about image processing on the boundary. And I think I may have discussed it in class and assigned it in class, but I don't think I ever had an opportunity to lecture on morphological image processing. You know, sometimes you just have to try different things and see what works. I liked the thresholding. That worked pretty well. Here's a dog. If I use yeah, that's not bad. So use the dog and then threshold the dog. What does that buy you? There. Now, how would you get a single pixel width wide edge on that? You could use one of the edge filters in through here, or not sure what this does. Ah, there you go. Apply. So that gives me a nice outside contour. That's an acceptable edge for our final. So I'll let you guys, you know, you gotta, it's, you know, this is the part about image processing that's kind of an art. You gotta kind of experiment. No one will tell you the best edge detector for your image, because every image is different, and I wouldn't expect anybody to have the same image that I have. It doesn't make sense. You wouldn't do that.
So why does it need to be like thresholded?
Well, I didn't threshold in this case.
Like for
I used the Wu quantization algorithm and reduced the number of colors to 2. Then I proceeded to threshold in order to go from 0 to 1, because I didn't want colors that were close to the colors that I was given. I wanted colors that were bi-level and also 0 or 1. So what I did with thresholding is I took colors that might have been like yellow or greenish, and I just said, okay, I want all those colors that are above a certain value to be 255, and all those colors that are below a certain value to be 0. And so that gave me a nice black and white image, which I could then proceed to use to create an outline. So I needed a binary image.
How do you get it? Because like for my image, I just use the logs. I convert it to gray, and then I just use the log Sobel. But like when I print the pixels, like those weird values.
You want a threshold then after your log Sobel.
Because like the edges themselves look really nice, but the pixel values.
So guide me through your process. I'll open up an image.
Well,
Okay.
it was like for this certain image is how it worked. I don't know.
Well, do I have your image?
It's uploaded from Blackboard.
Well, I'm not going to
Yeah.
go to Blackboard to get your image.
Yeah, I know. So
But if you could just tell me what you did, maybe I could help.
click gray, color,
Color, gray,
yeah, and then I went to filter,
filter,
edge,
edge,
log Sobel panel,
log Sobel panel.
and I made the kernel width as low as possible, and threshold was about 66. Like for my image.
The kernel width is as low as possible, and the threshold was 66.
A little less, yeah. It's less than it, but yeah.
All right, so then I hit apply. That's nice. That's nice. I like it.
Yeah, so
So then I said apply, and now I go. I mean, that's a good outline right there. That's a great algorithm. So now if you went to threshold, where would you go for threshold? Filter, thresh panel, and now you can adjust the threshold. Yeah, that's fine. So now you know every time you see the black outline, it's going to be completely black. Every time you see the white, it's completely white. If you wanted, you could negate the image.
So what would I want the threshold to be?
Apply it, and then you're there.
What would I want to threshold it to?
Well, right now, it looked to me like what you had was reasonably thresholded already. You might not need to.
Well, like for some reason when I printed the pixels, it was either -1 or like negative some other random number.
Oh. I don't know why that happened. But if you wanted to threshold it, you could threshold it until you get exactly white or black pixels, like I just did. If you wanted, you could negate it as well, and then apply it. That way, you could search for the white pixels and leave the black pixels in the background. So when the pixels are 0, you can ignore them. When the pixels are 1, you've got an x coordinate and a y coordinate, and that goes into your point list. You see. This is very good for the bug walk algorithm because it can walk completely around some large perimeters. But bug walk could take a while, and the brute force algorithm could too. So there's no clear answer on this one. But I liked your solution. You know, that's a real good solution. And you could certainly automate it. So now the question becomes, how would you extract the vectors? And then once you extracted the vectors, how would you order them? And then after you've ordered them, how would you save to an SVG file? Huh?
The ordering is
The ordering is hard and SVG is easy?
no, everything's hard.
Everything's hard.
Yeah. The edge detecting is easy.
The edge detecting is easy.
Yeah.
So let's follow this chain of thinking along to a logical conclusion. How do I save SVG files?
Did we talk about ordering?
You don't want to do the SVG files?
What should we do first?
I was going to do the SVG files next,
Okay.
because we already went through the algorithm for doing the ordering.
I didn't think that we really said how to do it.
I have a question.
Yes, sir.
So, we want our edges to be 1 pixel.
Single pixel width wide edges.
Yes, that. Now, what if we have an area that is filled?
Then it's not a single pixel width wide edge.
I don't know.
Right? If you have an area that's filled,
Yeah.
then you haven't got a single pixel width wide edge.
But will the laser cutter, be able to find that difference if we have a black and white image for example?
The laser cutter wants vectors. It doesn't want large areas. It doesn't know how to cut that. It wants an outline.
The laser's going to cut out that blank area, so it's just going to go around the edge.
You want the perimeter. Only the perimeter.
Yeah, but the laser's not smart enough.
Laser doesn't know anything. The laser goes to point X and Y, and it's either on or it's off. That's what the laser knows. So you can tell the laser to go to. In other words, when you output SVG in the standard format for this machine, you're basically creating a numerically controlled milling machine with a cutter. And you're directing the cutter around the perimeter of the thing you want to cut. So you must detect the perimeter, you must create a single pixel width wide edge around the perimeter, create vectors around the perimeter, order the vectors, and then output them in the correct order so that the laser will cut your outline.
Yeah, that end part is where I'm feeling not too confident about.
Right, you have to display them in order, but you also have to output SVG files.
How many?
How many files?
Yeah, how
Well,
many?
just one file for the entire image that you're creating.
Okay. So what if we use a tool that took our, maybe it's a JPEG and has a single width outline, and they converted it to SVG, or vector graphics, in scale vector graphics. Is that sufficient? Or
Well, no, because the SVG um, vectors may not be ordered.
yeah, that's the confusing part to me, the ordering of the.
Well, maybe we could discuss that after I have an opportunity to show you how to output SVG files.
Cool. Deal.
Okay, so what I have is a program called Test SVG Generation. And what I'm going to do is I'm going to run this program. I'm going to save this out to test.svg, save. And then what I'm going to do is I'm going to start up a program that can read SVG files, and I'm going to use the open source public domain program called Inkscape. Inkscape is a program which is available for Windows and Unix and the Mac, Gesundheit. And it should be able to open up the test image, and there it is. I'll give you another example of a program that outputs SVG files. I've got a program called Book Examples Chapter 26. I believe it's called Draw 2D. And if you run the main method in Draw 2D called Draw Main, it'll give you a draw program which has the ability to save in SVG format, if memory serves. So here's some vectors. We'll draw a square. Oh, here, let's draw an oval or a circle. And then we'll shoot a ray. And now what we'll do is we'll export as SVG. Yes, sir.
What is an SVG?
That's a scalable vector graphics file. So it consists of vectors, just like the vectors we want to output to our laser. And Inkscape can output to the laser directly, so it's very nice if you can import these things using Inkscape so you can test your SVG output. So let's call this ray.svg. We'll save it, and then we'll start our little Inkscape program and open ray.svg, and there it is. So this is a vector in every sense of the word. What it means to me, the user, is I can select items and I can ungroup them. Then I can select other items in the vector list and move them around. In other words, the primary advantage of a vector is that I can edit it. I can change the font. I can change the color. I could change the speed with which the laser etches this vector. I could, make it so that it engraves instead of cuts. I can do all kinds of interesting and wonderful things with the vector.
Is it just like a random thing?
I beg your pardon? Is it random?
Yeah, what is that from?
What do you mean, what is it from?
Like, what does that do?
What do you mean, what does it do? It's just a picture.
Oh, what?
It's a picture of something I drew. I don't understand the question.
Why
Okay.
is that useful? That
Why is a picture useful?
That
It conveys information.
is there anything useful about that?
About this picture? No.
Yeah.
I just drew it out of randomness. I decided to draw a picture, and then I decided to export it. See? I can clear it if I like, and then we could draw some other picture. Like here's a sine wave. Now I can export the sine wave as a vector. I can make lots of sine waves. Or if I wanted to, I could draw a triangle. It's just a draw program, really. Or I could draw... Here, I'll draw a lens. That's a plano-convex lens. In the case of drawing the circle, when I draw the ray, I was able to fire the ray through the circle in order to show how an index of refraction would cause the ray to bend and then bounce. So I'm trying to model what a 2D geometric optical system would do. So all it is a modeling program which is working with vectors. So it's just a program that I wrote to kind of demonstrate how you can use Java 3D. You can double click on objects, and if they're editable, you'll be able to alter their scale. You can do affine transforms like rotation. You can scale them in different dimensions. You can shear them. And then after you're done applying all these affine transforms to the vectors, you can save them as SVG, test2.svg, save, and then you can run Inkscape and open up test2.svg, and there it is. And there's a zoomy thing here. Zoom. Oops, I zoomed too much. Zoom out. So now in the SVG, I've got another object which I can ungroup, and now I can grab individual sine waves and move them around. And you could say, yeah, why is this so useless? I don't know. I just thought it was fun, for no particular reason. But you can definitely design things in Inkscape or with the Java program and output them to the laser. But because we're doing an image processing program, I thought it would be better for us to start with images. So what do you think of that? There's a file menu in my draw program, and if you chase it down and look at how export SVG works, what it does is it goes to the component that you're interested in saving, the one that can do drawing, and it calls clipboard utils save SVG. And you might want to take note of that. So call clipboard utils save SVG and pass an arbitrary component, and it will output an SVG file. So if you can draw it on the screen, you can output the SVG file. Yes, sir.
But is the SVG file ordered?
No, this is just generating an SVG file in the format.
So we must order it first.
Order the vectors when you draw them on the screen, and then save it to the SVG file.
Okay. So, question. All SVG files have this kind of data that says the order in which the vectors are drawn?
Yes. In fact, if you go into the command prompt, you should be able to edit the SVG file directly. If only I knew where I put it. Oh, here it is. Emacs foo.svg. What's that look like? So now what we're seeing here in the SVG file is a series of strokes, where the strokes are given different colors and transform matrices, and they're just line segments. And here you can see the line segments: x1, x2, y1, and presumably, yeah, there's y2. So SVG files contain a series of line segments in a specific order. What do you think of that?
What if we wanted to do the hard way and just write it like this?
Oh, you want to output SVG files directly without using Java to draw them first?
Yeah, just writing them by hand.
By hand?
Like this code, just replicating this.
What do you mean writing them by hand?
Basically defining all the vectors that exist.
Are you going to do the edge detection by hand? I got confused. I don't understand the question. How do you do edge detection by hand? You mean you're going to print out the image and you're going to trace it with a pencil?
No. Essentially not doing edge detection. Essentially just generating an SVG file from this. Like generating this file by hand. And bypassing the edge detection.
I don't understand how you generate a file by hand. Don't you need a computer to generate a file?
Couldn't I just write this?
You mean like on paper with a pencil?
No, on a
How does that work? I don't understand.
on a computer.
It's a data processing problem. So the data has to go into a program and then come out from the program. Right?
What are we looking at here? SVG file, right?
Yep.
Yeah. So I'm talking about generating my own SVG file. That's ordered because I coded it myself. And I defined all the lines that exist in this SVG file. And I drew my picture by just generating the SVG file from scratch. By typing all these definitions of line x1 and finding them and putting them and saving it as an SVG file.
What is wrong with you? I don't understand where this is coming from. Did you want to use Ruby on Rails with that?
No.
Okay, let's move on. The answer to your question is, if you want to do the whole thing in Perl or Ruby on Rails or some other wacky thing that you've come up with, I have no objection. And I'm not exactly sure what doing it by hand will entail. But I'm convinced you've selected the absolute hardest possible way you can do this problem.
Okay.
I don't mean to be. If you want to go down that path, I'm not going with you. But it's okay. I've given you a utility which will essentially take an arbitrary component upon which you can draw an arbitrary set of vectors or polygons, and it will save it to SVG format. And it's using an SVG generator, which is open source and is capable of generating standard SVG files according to a World Wide Web Consortium document. So it is a standard file format output. If you can find some other way to output it that's better than that, go for it. How's that? You may find that there's a perfectly good library in Ruby on Rails that lets you output SVG files. I'm sure there is. I'm sure there is. I'm convinced. So here's where I'm at. Okay, I have graphics.clipboard, and graphics.clipboard has these utils, and clipboard utils lets you output SVG files that you have drawn on the screen. So in the boundary frame, I've got this component here, right? And if I wanted to output SVG files, presumably I could go to this component, this container, or the closable frame, whichever you prefer. I guess the container would be the way it's at. I could insert clipboard utils dot save SVG and pass in an arbitrary component like this container, C. And what's his problem? Add exception to method signature, and there you go. So now the question is, when would you do that? And my answer is, I don't know, probably right about here, after the print statement. And I don't know, maybe I should use closable frame instead of container, I'm not sure. See, display image is displaying the actual output. The bug walk is working on the output image. Then comes the polygons. Maybe the output image would be a good place. I don't think I want the input image. Output image. Dot get. Oh, he won't let me get the component off of that. So maybe I gotta work with the I'm not sure. I'm gonna try the container. I'm not sure exactly what's gonna happen when I try and save this container. Now he's complaining. What's he moaning about? Okay, so now he's moaning about this. Surround with try-catch. How's that? He's okay with that. Okay. He just wants to throw an I/O exception if he can't get the file. So let's just run it. See what happens. I'm not sure what's in the container. I think it's the original input image and not the image with the outline, but I could be wrong about that. So he wants to do a save. I guess this is bolts, bolts dot svg, save. You see, this says before. I think I got the single pel thing instead of the before thing. That can happen. It's called bolts svg, and it should be an Inkscape document. So if I run Inkscape, we'll see what I output. I'm not real sure. File, open, bolts svg is here. Open. Oh yeah, you see it's the original image. It did save it, but it saved it as a raster because I didn't save the right image. Let's zoom in and see what that looks like. Oh wow. Oh no, I got the outline as well. So in fact it saved the whole thing with the image and the outline. So that's pretty cool. So if I wanted to just get the outline, I wouldn't have shown the original image. I like showing the original image because I can see how close my my polygons are to the original image. There's definitely issues, but some of it should be editable. Let's see. Can I zoom out here? Let's zoom out a little bit. And then go into the selector and ungroup. What does that buy me? Not much. Let's ungroup again. There you go. There, that's a whole vector. Right there. It's a connected vector. It's pretty cool, actually. Here's another one. Right? These little green outlines, these are great. You can edit these. Oh, there you go. You can take away the raster part, and you can see here's the only part that's left is the outlines. Can you get that background out of there? Yeah. Cool. So if I had just drawn the outlines, that's all that would have been saved. Just the green part. So how come it's drawing the original image? I don't know, but I could tell you this. If I wanted to, I could just take these polygons and draw them inside of my closable frame. So I could create a closable frame that has nothing but the polygons in it. So this closable frame, CF, is titled before. He's adding IP. IP is the image process listener that draws the polygons. There must be some other place in this program where an image is being drawn. And it's probably right here because you're drawing it on the output image. Bug walk output image, display single pixel width image. I don't quite see where the closable frame CF gets the input image. Right, so here's the input image. Oh, I see. It seems like the input image is being used in more than one place, right? Or maybe not. Here's input image gets me the output image after a threshold. I get the single pixel width wide image. I do a display image, I get the single pixel width wide image. I get the output image, I put it into the bug walk. I get the polygons with the bug walk, and then I call save. So, end of the day, I'm not convinced I know exactly where that image is going, but if I wanted, I could create a new frame and draw the polygons in that frame. And I suspect you guys would know how to do that as well. Does that sound right? I'm not hearing a yes. I'm not hearing a no. Would it benefit you to see me create a frame and draw polygons on it?
No.
No. Okay. Then I won't do that. At the same token, there were still some outstanding questions. How do we order the polygons? Right? So now I've got these wonderful polygons. And the first thing I would do is I would say, okay, what are we using for polygons here? For my polygons, I have my own little data structure. Polygons consists of a vector which acts as a container of polygon. A polygon is a class that I have in the Java AWT class, and what it does, I don't know if you can read this, it's a little small. It gives me a series of line segments which are defined by points. Each one of the points is put in order, and the polygon can be either open or closed. An open polygon doesn't close the first point with the last point. A closed polygon does. And so all you're really doing when you have a polygon is you create a point list. And if it's an open polygon, you just keep adding points to the list. Well, that's perfect for us, because what you then are seeing when you're looking at a series of vectors is a series of vectors that can be stashed into a single polygon, which in Java is a built-in. So the polygon shape is something that you can pass into the draw context, and you can just call draw on it. So what happens to me, the programmer, is I have relatively an easy time of drawing the list of polygons. So here, if somebody passes in a graphics context, I can set an arbitrary color. That's why my polygons are being drawn as green. And then for each polygon in my vector, I can call draw polygon. And the draw polygon gives me an array of points, x and y, and the total number of points. And it's really just drawing a series of line segments. So then the question is, how are you going to order your polygons to minimize the amount of time it takes to do your draw? And that's where we get into this algorithm in here. Doug's dumb brute force algorithm. For each of the polygons in the list of polygons, you want to reorder the list to minimize the amount of time it takes to do your draw. So now we can rephrase it. In Java, given a list of polygons, find a way to order the list to minimize the draw time. So now what I can do is I can guarantee you that you won't always be able to get it so that one polygon is a minimum distance away from its tail relative to another polygon, but you can at least search. So for each polygon in polygons,
Is a polygon the same thing as a vector? Because we were talking about vectors
no, a
before.
polygon is a list of points. You just left the room when I mentioned it.
Oh, sorry, I must have got it.
That's okay. Polygon is a list of points. So, I beg your pardon?
How is that related to the vectors?
Well, the vectors are arranged end to end in a single polygon. So, I think it might have been lost on you or something, but maybe it makes sense to try a little polygon example. I don't know.
A lot is lost on me right now.
Well, what can I do to fix that?
I don't know, I'm thoroughly confused. I couldn't even make sense of the point.
You're thoroughly confused.
Yes.
Okay. Can you tell me what a polygon is?
Yes. It's a list of points from vectors that are arranged end to end.
Okay. Could you draw a polygon? Don't know.
That's the part that kind of confused me.
Alright, so let's do a single draw polygon example. New Java class, polygon example. Okay. So to start, what I would like to do is create a polygon. So in my polygon example, I'll create a closable frame. I will set the size of the frame. And I will set the visibility of the frame. And then when I run the program, I would expect it to display a frame. So we're all good with that, right? So there's my 300 by 300 or 500 by 500 frame. So now let's take this frame and get something upon which we can draw. Right? Well, I'd like to draw something in this frame. Perhaps we could use a panel. So we'll create a J panel, which we'll call our poly panel. Poly panel class poly panel extends J panel. Okay. And has a paint method that takes graphics as a context, and then in the graphics context it draws a line. And the line starts at 0, 0 and goes to 500 by 500, and that's it. Now what we'll do is we'll make a new instance of the poly panel. We'll get a content pane. We'll add the poly panel using border layout. So we'll set the layout manager to be, I don't know, new border layout. And then we'll do c.add polypane using border layout dot center. And when the panel is created, poly panel will have a size, but I'm wondering if we need to set it. Let's just see if this will run. Yep. So now we've drawn a line. Got that? Everybody good with that?
Yeah.
Okay so far?
Yeah.
Okay. So now suppose I wanted to draw a polygon. Let's create a polygon in the poly panel, because that's what this is all about, right? Polygon P equals new polygon. And it says here I can take a number of points, x and y, and I can pass in whatever number of points I want, or I can add points to the polygon, whichever I prefer. So let's start by creating a polygon, and then we'll create a little constructor for our polygon panel. And then we'll do p.addPoint, and our first point will be 0, 0. And we'll add another point, p.addPoint. We'll make it 20, 45. As a matter of fact, I could probably add 100 points or something, but that's add one more point, 45, 50. And we'll add another point. How about 500 by 500? And now when we draw the line, we'll also draw next to it g.draw polygon, and we'll pass in the polygon P. And that's it. So that'll draw the polygon. So polygons are built in. They're part of the Java AWT. A handy data structure to have around. And so now you can sort of see, here's the original line that we drew, and here's the polygon with its little deviations coming away from the line. Got that? So that's clear, right? Everybody's good with polygons? So if I get a series of points, XY points, from my image, because I've edge detected, I can create a whole pile of polygons. Now, I can't just make one, because the points won't all be connected. But I can, for the connected points, make one polygon. If the slope changes, that might be okay, but if I'm trying to make vectors that are kind of far apart, I'd like those points to be as far apart as possible. So as I get the series of vectors, if they're connected, I can make a series of polygons. And then all I need to do is order the polygons to minimize my draw time. So what I've provided for you here was a polygons class, which is a container of polygon. And so what that does is it'll give you back an array of polygon type, where all the polygons are homogeneous. And if you like, you can order the polygons from that.
Do we have that? Where is that?
Polygons is in IP.transforms. It's probably not a great place for it, but that's where it's at. If you're ever looking for something, you can do a edit find.
Yeah, there were two.
I beg your pardon?
There were multiple polygons.
There are?
Yes.
Find in path polygons. So you can see where it's being used. I don't think it's being defined here. I'm not sure if there are other, maybe I should have done something where I said class polygons. Find, I want to find in path. Class, lowercase, polygons. And make it case sensitive. It's only in one place. It's used in multiple places, but there's only one class polygons, as far as I know. There shouldn't, it's possible there's more than one, but there shouldn't be. I really only need one. Let's see what else. This will let you do stuff, like it'll let you draw the polygons, you can print the polygons, you can get their average, you can get stats. Yes, sir.
So easy example, let's say my shape is a triangle. That's my image. This is an edge detected triangle. That represented by a polygon. It's ordered by the order the lines are drawn, correct? If I'm defining a polygon, I'm going to define it first at the top of the triangle, then I go to the right of the triangle, to the left part of the triangle, and then close it. It's ordered by the way that I said, go there first, to the right, then across, then back to the top.
Correct.
Okay.
That is correct. In fact, now that I look at it, there's even some stuff in here, next closest polygon. So there's a way to search, given a polygon, the entire list of polygons, so that you can proceed to find the next closest polygon.
Is that yours, or is that from AWT?
No, that's me.
Okay.
That's me. So this has got some helper stuff in it that may or may not be of any help to you. This will give you the distance between two polygons. And this will take a short image bean and build a polygon list. So you can take an arbitrary image and build a polygon list out of it. Presumably, the image has been edge detected already. I don't see how build polygon list could work without an edge detected image. Let's just make sure. Yeah, not only is it edge detected, but it assumes that all of the edges are on non-zero values in the red plane. It ignores green and blue. So it makes a few assumptions. It assumes the background is black and the foreground is not black. And also that it must be black in the red plane. So that it effectively says the value of red must be 0 in order for it to consider it as a non-candidate. So it must be non-zero for it to be a point on the polygon list.
That's the trouble of having to list the vectors and order the vectors.
Well, ordering vectors is still a
listing,
yeah,
like having
listing.
to gather the points.
Yeah.
First.
I would test this code first. Short image bean. Let's see, polygons. Let's see, how does this work? He says build polygon list needs a short image bean. So I would do the following. I would create a main method in here if there isn't one already. And there isn't. So I would open up an image in the main method and call build polygon list, and then draw those polygons. So if you've got a polygon example over in here, then you probably want to get an image and display it. I think I may have done that work already. Here's an image. I'll go to the polygon example, get my little image. Just call image utils and display it. f.getName. So that should show the actual name of the file as a string. And just the file name, not the fully qualified file name, in the image header. And there it is, hardware.gif. So then what I would do in a case like that is I think you got to negate it. Image utils dot negate, because the background has got to be black and the foreground where the edges are has to be white. And Kyle, what was your algorithm? You want to do the log Sobel? That sounds good. So then image utils dot log. See, I don't see that here. Is Sobel in here? Oh, there's Sobel. I don't want to just do Sobel by itself, though, right?
It was quite different.
I mean, if I just do Sobel by itself, I don't think that's going to buy me anything.
What if you assume that you started with the edge detecting?
Oh, wait a minute. That wasn't bad. That's pretty good, actually. I don't know if it's a single pixel width wide edge, but it's not bad. Right there. And now, it was polygons that was doing this for me, right? Polygons, polygons, P equals new polygons, polygons, and what is this? Alright, so then P dot build polygon list with a new short image bean of image, and I'm not sure what the XY business is for, but let's do the following. Let's take short image bean, SIB equals new short image bean, Alt Enter. Well, let's try that again. Alt Enter. There you go. And now if I put SIB in there, maybe I could do something like SIB.get width, SIB.get height, and what does that buy me? Oh, my polygon panel needs the polygons. Shoot. I gotta pass the polygon panel the polygons. So let's give it the polygons, and pain in the ass. Let's just run this first and make sure it works. This is going to compute polygons, but it's not going to print them. Very good. Don't trust this program. There's something going on here. I'm not quite sure what the issue is. SIB of XY. What was the X and Y for? Oh, he's adding points X and Y. Oh. Yeah, that's garbage. Don't use that. I don't know why that's in there. I'd have to do an analysis to find out why that's in there. I like my boundary utils bug walk better. Polygon example. There it is. Where did we go wrong? Polygon panel was fine. We went wrong when we went to polygons and tried to do build a polygon list. That was no good. Up through here we were okay, because that just gives us a Sobel. Just checking. Yep. So there's the Sobel edge detector. Whether or not that's a good enough edge detector for your application, I don't know. I think you had said something about doing a Laplacian of Gaussian. No? How did you do it? Log Sobel.
Oh, is that? Oh, okay. Yeah, that's what it stands for.
I think so.
Does it? Okay.
I think it's a Laplacian of Gaussian, but I might be wrong. Log LOG, Laplacian of Gaussian. Image utils dot Laplacian. Yeah, I'd have to do a search to find out where that's at.
I think for the homework you said to just do it out. You can do it external from the actual code.
You can.
So then we can assume that we start with the edge detector, right?
Yeah, I'm just thinking out loud. There's got to be a place in the code that does the Laplacian of Gaussian that you were interested in, and I was going to find it. And I'm thinking it's in the Edge menu inside of the J2D .GUI package. So if you went J2D.GUI menu and you looked for like the Edge menu, which is here, somewhere in this Edge menu, is that what you were doing? Laplacian of Gaussian Sobel? So that panel, you said you set the kernel width to something like 2, and you did the threshold to something like 128?
No.
66 and 4? So, I mean, what you can do is you can get the Laplacian of Gaussian Sobel processor, and you can grab a hunk of that and put that into your polygon example. So when you get a processor, it's an image processor interface implementor. So you can say new log Sobel processor, and then your kernel width you said was like 2, 4, and sigma might have been something like 2, and threshold was probably something like 56, and is threshold on is yes, and is Sobel is yes. And now if you wanted to you could probably take away this Sobel thingy right in here. You could take away the negate thingy right in here. You can get your input image. So all this does is it reads in from a file, gets me an input image. Now I want to take that image and I want to process it with the log Sobel processor, log.process image. And that will give me a new image, image, which I will replace using your algorithm, Kyle. And now we'll display it. What could possibly go wrong? Oh, that looks nice. It's nice and connected. It's got a little flat top. It's not bad. I'm good with that. That's very nice.
And that's where my file goes down.
What would happen if I changed sigma to like 1? Would I get a little more detail? I can make this like 2, right? Yeah, you do get a little more detail. You get the rough edges around the threads. But you also got a little speckle on the side. But that's okay. I mean, you did pretty good. Make this a 4 and you'll probably get rid of that speckle. Make that a 2 and you'll get rid of the speckle. So there's lots of good ways to do single pixel width wide edge detection. You may have to mess about a bit. That's why I like an interactive program better. Because once you know what the parameters are, you can just hard code them in. So the log Sobel processor is an implementor of the image processor interface. And the image processor interface has the process image requirement. So that means that when you call process, an image goes in and an image comes out. It's a standard data processing interface. So by using that standard data processing interface, what you're really doing when you create the log Sobel processor is you're creating an operator. And you can parameterize the operator with the arguments that are passed into the constructor. So what do you think of that? Good, right? If you wanted to, you could look at the border frame now, and you could assume you've got your single pixel width wide edge. You could do your boundary utils, and this is why the input image gets drawn over by polygons, because he calls super.paint. If I got rid of super.paint, it would just draw the polygons without the input image. I just noticed that. I was trying to figure out, where did that image get drawn? The image panel process listener actually draws any image you put into the argument. So now he's going to save it into bolts. Bolts 2. And there it is. No image is being drawn in the background. So that's kind of cool. If you just wanted the boundary utils in your little polygon example, you could grab those and then invoke the get polygons off of boundary utils. Paste boundary utils bu.getPolygons. So you got to start with an image. And call bugwalk, do your boundary utils. You can get your polygons, or you could just call print polygons.
Which one would we want to use, the boundary frame or the polygon example?
Well, right now I'm just doing a
Like, I don't get what like, doesn't the boundary frame get all the polygons?
boundary utils is getting the polygons for me. Boundary frame is using boundary utils. So boundary utils is where I did the work. That's where the heavy lifting is at. Presumably this will edge detect it and print the polygons, although I'm not sure if boundary utils wants oh, it's printing them onto a laser printer. Oh, that's the wrong kind of printing. There must be another way to do this. Draw polygons. Draw polygons wants a graphics context. Get polygons. What does that return? Polygons. Polygons, polys, equals. So now once you got the polygons, what can I do with them? polys dot print. Let's try that. I wonder if it's going to try and print them onto a laser printer. That would suck. Nope, it prints them out. So it got a bunch of polygons. So that's pretty cool. The polygons aren't ordered in any particular way. You still have to order them. And I think that this gives you kind of a jump start. What I could do is I could take this little chunk right in here, polygon example, and I could send that out to
Can you upload it like you did yesterday?
yeah, I could, what would be good is if we put it into a zip file, I think, right?
Yeah.
So how
Updated boundary frame also, because we changed a little bit.
all right, so maybe we need to put Well, it's difficult, but don't we need to put boundary frame and polygon example in the same zip file?
Yeah.
But they're in different packages.
You found them. Didn't you just
Huh?
Didn't you just duplicate them yesterday, or?
Well, they're kind of duplicated here. I could take this main class, rename it, and then move it into the polygon example. Maybe that would help. So let's do that. We'll call it the boundary frame test. And what we'll do is we'll move it into, oh, he needs to get single pixel image. We'll make it public. And then we can move it over to polygon example, I guess. Polygon example. How's that? So now polygon example has the boundary frame test, and it has the poly panel. How's that? That all right? So now I've got polygon example in book examples, chapter 26 graphics, and source, book examples, chapter 26 graphics, polygon example. I will make a zip file out of it, polygonexample.zip. Take the polygon example, cut it from here, put it into the line directory, and then upload it to the final. Now, what can I do with this final? Edit. Edit final. Attach file. Lion. Polygon examples. Where is it at? Here it is. Open. And submit. How's that grab you? So there's the attachment.
So where's the part with the Inkscape come in? Or does that not?
Well, Inkscape is used for reading in the SVG file output. So when you're done, you should be able to open your file with Inkscape.
Okay. But like that example should save it as SVG.
SVG.
So then once we order the polygons, what are the next steps?
You got to save them as SVG.
That's it?
And that's it.
We're done.
Yeah, you want to display it on the screen and put it in your submission packet, right? So presumably you'll paste the image into a Word document or something. If you like Microsoft products, because I'd like to see the picture. You might be able to put the whole thing into a zip file if you want. I don't know how you like to package these things. Everybody has their own preference.
So like, other than what we have here, we really just need to
What are the vectors?
because that's going to auto-generate the vectors for us.
Well, I have a way to get vectors, and you can certainly use my algorithm if you want.
We don't need to anymore directly explicitly use this algorithm.
Well, the XY to vec algorithm that I have in BugWalk is not ordering the vectors for you.
Okay.
So you
But
still
it does generate them.
It does generate vectors. It generates polygons.
Okay.
And it puts the vectors into a list of polygons. Is that an efficient list? I don't know. You might want to check it.
So like what
minimize plot time, you mean?
Yeah, but like
You might like to order them end to end. I like that. I mean, yeah, I use this distance metric where I look at the distance between one polygon and all the other polygons. So that's a way to go. If you look at the last point in the polygon and compare it against all other polygons, and you know, their heads or their tails, that could be an indicator. So you're computing the distance between one point and the head or tail of a polygon. That should give you a minimal plot time, or at least reasonably small plot time. Any other questions? Okay, well, good luck. This is due on the 2nd of May, which is soon. Today's the 24th. I think there's only 30 days in April. And then, so we're really dealing with Friday a week from tomorrow.
yeah, we're screwed.
So good luck. If you got some questions, you can shoot me an email, and I'll try and send the email out to the rest of the list. I think we got shortchanged this semester because they had us miss a class last week, which is really unfortunate. Thanks a bunch. Have a good evening.